let's talk about another concept called vapor pressure that's closely related, again, to this idea of vaporization and energy required to vaporize and so on. Okay? So what we were talking about before was an open container. Okay? If we have water that's allowed to vaporize, okay, just out into the room, or if you're heating it or cooling it, whatever, how that happens. Okay? But it behaves much differently in a closed container. Let's say we have this container A over there that has water in it, but if we were to hook up a pressure gauge originally, to have this figure here, we would have to start with a vacuum. And this value, 0 millimeters of mercury, that would be a reading of the initial vacuum pressure. So we're assuming that we started with a pure vacuum in there, and then we had some water down below it. So really the only way to do this would be to start out with an empty container that was evacuated, and then inject liquid water into it like that. Okay? At the moment we inject that water, okay, we would be at 0 millimeters of mercury before any of that water got a chance to vaporize. Okay? But what's going to first start to happen is that those water molecules will start to vaporize, okay, assuming that we have enough of them, assuming that we have any of them that have enough energy to vaporize. Okay? They'll start to vaporize. But then the pressure increases. Okay? This 10 millimeters of mercury would be the pressure of that gas up above the liquid. That's called the headspace when you have a closed container. The vapor that's in the space above the liquid in a closed container, that's the headspace of a container. Okay? So that pressure will increase, okay? But now as we're collecting molecules up in that headspace, some of those might bump into each other or bump into the sides of the vessel. They may decrease their kinetic energy as they're flying around. And if that happens, and one of them sort of makes its way to the surface, it could fall down onto the surface and then get stuck there, right? Because now it's interacting with those others around it, and it may not have enough energy to fly away again. Okay? So these downward arrows, okay, come from condensation. And eventually, we'll get to a maximum pressure, okay, and that only happens when the rate of vaporization, rate of vaporization equals the rate of condensation. Okay? Where we have the same number of up arrows as down arrows. For every molecule that is flying away, another molecule is landing on the surface. Okay? And as soon as that happens, we will no longer be increasing the pressure up above. We'll sort of reach a maximum pressure. Okay? And the two opposite processes with equal rates will keep this pressure constant. That's referred to as the vapor pressure. That's the vapor pressure of water at 25 degrees C. If we change the temperature, we're changing the ratio of molecules that are able to vaporize, so the vapor pressure ends up being different. Okay? So, starting with a vacuum, the water molecules will vaporize, but as we get more vapor molecules, we actually have more condensation that happens, and that condensation continues to increase until those two opposite processes are the same. Okay? When those two opposite processes are the same, that's called dynamic equilibrium. When we have equal rates of opposite processes, dynamic equilibrium leads to constant pressure in this case. Concentration if it's a solution. Okay? So this little diagram right here, rate of evaporation will be constant for a particular temperature. Okay? So that's only dependent on the substance and the, how well the molecules can fly away. So evaporation is always going to be happening. They're always going to be flying away. We start with no condensation because there's no vapor. Okay? But as that vapor builds up, we get more and more condensation until their rates are equal, at which point we've reached dynamic equilibrium. And vapor pressure is the pressure of a gas that's in dynamic equilibrium with its liquid, okay, in a closed container. Okay. That also means that if we have any liquid water present in a container and we hook a vacuum pump up to it, we can never pull a vacuum any more than 23.8 millimeters of mercury. Okay? If we happen to temporarily get more of a vacuum, we would just have more vaporization than condensation, okay, at that particular point, and the pressure would increase back to that sort of constant point there. But in actuality, what it would look like if you started with an open container, you would have air, okay, up there. So you'd have 760 millimeters of mercury of air up there. Hook the vacuum pump up to it, pulls off that air as well as some of the water vapor in there. That pressure would decrease, okay, until it sort of reached that minimum. Okay? It would be coming at that from the opposite direction. But we wouldn't be able to get below 23.8 millimeters of mercury then. So anytime we have a liquid at equilibrium with its vapor in a closed container, that pressure is going to be predictable. So turns out any system that's in dynamic equilibrium already, it will respond to a disturbance in that equilibrium in whichever way will cause it to restore the equilibrium. Okay? So let's start here. It's a different substance. That looks like hexane to me, but it doesn't matter. Okay? We've got a liquid. We've got its vapor up above it, and they've been allowed to settle into equilibrium. So the vaporization and the condensation are happening at the same time, at the same rate. Okay? We'll have some sort of vapor pressure that's constant over there. Okay? So let's make a little graph just right in this little empty space here. Okay? Pressure on this axis, and then time going this way. Okay? So if we're at dynamic equilibrium, the pressure is going to remain constant. Correct? Okay? But now, let's say we get over here, and we all of a sudden, this is a plunger that we can move. Okay? We all of a sudden pull upwards on that plunger. Okay? We increase the volume. What should happen to the pressure just from that? Yeah, we'll decrease the pressure. Okay? So right here, the second we pull that plunger, pressure is going to decrease like that. Time. Right there, we pulled the plunger. Pressure will decrease because now we have a larger area for that same number of molecules to be banging against the inside surface, right? Okay. But look what happens now. Okay? We're still vaporizing at the same rate, but how come this arrow now is smaller? What do you think? Pressure has decreased. We've got the same number of molecules flying around in a bigger container. Okay? It's going to take longer for one of those to come back and find the surface, right? Okay? So right here, what happens? Condensation rate decreases. Okay? We're still vaporizing the same, but now we won't be condensing as much. So what is going to slowly start to happen to that pressure because we're not condensing as much? Pressure is going to start going back up. Okay? We're going to start replenishing this supply, okay, in there, and it's going to go up until we have enough molecules now in this larger volume that the condensation rate and the vaporization rate are the same. So what's going to happen here to pressure, it's going to start going up, and it's going to do something like that. And it's going to reestablish the original pressure that we had before. Okay? That original pressure was the vapor pressure. And then once we get to maybe about that point again, the vapor pressure is back. Okay? We're back at equilibrium again. Equilibrium means those two opposite processes are now back at the same rate. Okay? So we've got much less vaporization happening, so less of those falling back down. We'll build up the concentration up here until we get more and more of those vaporizing until it's equal again. Okay? What's going to happen to the pressure the instant that we decrease the volume? So I squeeze down on that plunger. Pressure is going to shoot up. Okay? Okay. What's going to change in the vaporization and condensation when I push down on that and I shoot up the pressure? What's going to change? And the arrows on this one are a little bit misleading. Just what do you think? If I've got now all my headspace compressed to a tiny little bit, yeah, condensation increases. Okay. This blue arrow on the left is smaller for some reason. That should be really the same as before, right? The vaporization is the same in all of these. That just depends on the liquid. Okay? Condensation increases. Okay? So now all of a sudden we've got a whole bunch of gas that's right there. We're gonna have a lot of condensation happening then until we reestablish that equilibrium again. Let's try that a little better, like that. See that? Vapor pressure. I'll just set until EQ, until equilibrium is reached. Okay. So that's what we mean by saying that a system will respond to a disturbance in its equilibrium, in whichever way will cause that equilibrium to be restored. Okay? That's how equilibria behave. This is a preview of an entire chapter on equilibrium that we will have 2 chapters from now. Okay? But this is just behavior of pure substances, how the liquid behaves with its equilibrium headspace up above it. Does that make sense? Have that little picture in your head. Make sure you can understand or explain what's happening with those molecules in there, how they respond to headspace. Increasing temperature. What did we say increasing temperature does to those molecules? Yep, increases the rate of evaporation because increasing the temperature gives them more kinetic energy. That means more molecules have that critical amount of energy that they need to vaporize. Okay? So we sort of increase the proportion like we see on there. Okay? So increases average, so it increases average kinetic energy. Rate of evaporation increases. Okay. So if we compare two closed containers, at equilibrium, at the low temperature, we've got a low rate of vaporization, so maybe only a couple vaporizing, and at equilibrium, we'd have to have the same number condensing. At high temperature, we'd have a lot of vaporization happening, but we can also have a lot of condensation happening. So we can have equilibrium in both cases, okay? But at that higher temperature, how would the vapor pressure be different? What would the pressure be up here compared to the pressure over there? Yep, higher pressure, vapor pressure increases. Okay. So it's still like a, sometimes I like to think of equilibrium like, one of those rotating doors where you've got people outside the room and inside the room. But if it's like a rotating door, you could have one person going in at the same time one person was going out, okay? And that would continue happening. But that's sort of different from how many people are totally inside versus outside. So, alrighty, let's look at this graph right now, because this actually relates vapor pressure, temperature, and boiling point. Okay, but we have to take a second to just have a look at what this graph is actually showing us. Okay, so let's just start with the water. Okay, the red curve that's over there. This is a graph of vapor pressure versus temperature. So just like we said, increasing the temperature will increase the vapor pressure. It is not linear. Okay, it is sort of a curve. We would get a curve like that from graphing by doing natural logarithms of things. Okay, but it is sort of an increasing relationship. Higher temperature means higher vapor pressure. Okay? Look what happens when temperature gets to 100 for water. Okay? This is 20. This is like room temperature down here. Okay? Increasing, 80, 90. Here's 100 C. What's special about 760? That's torr. That's the same as millimeters of mercury. Yeah, that's 1 atmosphere. Okay. So, boiling point, read this definition right here. Normal boiling point is the temperature at which the vapor pressure equals the external pressure. Okay. So, if we now have an open container, again, like this coffee pot here, we got 1 atmosphere externally. Okay. We've got 1 atmosphere of atmospheric pressure pushing downwards on that water. Our heat source is down here. Those water molecules are moving faster and faster. We could get water molecules that are moving maybe fast enough to vaporize, but if they're at the bottom of this container, any bubbles that form can just be collapsed by the 1 atmosphere worth of pressure on the outside. Now, bubbles down here will only start to form when they have enough pressure inside of them to be able to not collapse from the external pressure. So we need 1 atmosphere of water vapor on the inside of that bubble. Okay? And that only starts to happen when we reach, for water, 100 C is the temperature required to get enough kinetic energy for 1 atmosphere bubbles to form. Okay? If we only have enough for 0.8 atmospheres, we're not going to form bubbles because the atmospheric pressure pushes down and keeps them from forming. Okay? So that's when boiling happens. Okay? When we have enough vapor pressure to actually form gas within the interior of the liquid, okay, that survives being crushed by the external atmosphere. So let's look carefully then at this graph right here. Ethanol and diethyl ether are compounds that have significantly weaker intermolecular forces. Okay. So let's look at just like 25C. Let's draw a dotted line over here. Okay. This is room temperature. Okay. Let's write that there. So if we're just looking at room temperature, what we talked about before is still true. Here's water's vapor pressure. Here's something with weaker intermolecular forces. That's ethanol. Okay? That has higher vapor pressure to it. Okay? Weaker intermolecular forces means more molecules flying around in the gas phase up above it. Okay? Something like ether has a very high vapor pressure. Okay? If you ever work with ether, you'll know that. You can smell it immediately when you open the container because its vapor pressure is so high. The molecules just fly away. Okay? So because of this increased vapor pressure, as we increase the temperature of ethanol, it's going to reach 1 atmosphere sooner than water does. And ether, it's going to hardly take anything for that to reach 1 atmosphere, just 35 C. Okay? So higher vapor pressure lower normal boiling point. You know how that works? Ether's boiling point 35, ethanol's boiling point 78. Now look at ethylene glycol. I had said glycerin before. Ethylene glycol behaves very similar. Okay? No measurable vapor pressure at room temperature. Remember we said it's non-volatile. We have essentially no molecules with enough energy to vaporize. Okay? Not until you get 60, 80, 100 that you can even get a measurable vapor pressure, but we're still nowhere near boiling. Okay? Boiling for that would happen somewhere over by the door, like that, if you're extending that graph upwards. Okay? But the other consequence of this is that boiling doesn't have to happen at 1 atmosphere. Okay? Boiling point is essentially when a substance, when its vapor pressure equals the external pressure. Okay? So how could I get water to boil at a temperature less than 100 C? If we wanted to, say, do 400, okay, we could get water to boil at 80. We could get ethanol to boil at 60. We could get ether to boil at room temperature. So only have to lower the pressure just a little bit. Okay. We could get water to boil at room temperature if we got down to this value that we already showed here, this 23.8 millimeters of mercury. Okay. Right here. That is the vapor pressure at. Okay. So, actually hooking water up to a vacuum pump that can get it down to 23.8 millimeters of mercury, that will actually cause the water to boil at room temperature. Okay? Now, it will actually get much colder because we said that boiling and vaporization is endothermic. So at some point it'll actually freeze as it does that. But if you keep it at a constant temperature, you have to keep sort of supplying heat energy into it. But you could keep it boiling at room temperature at a low enough vacuum like that. Kind of interesting. But all has to do with how those curves work like that. Any of you ever seen a hand boiler? It's a cool little thing. It has a little bulb on the bottom of it, maybe a little twist, and then a chamber up on top. There are a lot of ways that they can get those to work. Usually it's a combination of some low boiling solvent. They used to just have ether in them, and you didn't really have to do anything. Now they usually have an alcohol of some type in them, and it has to be at a reduced pressure in order for it to work, but not terribly reduced. You know, you could get it up to 30 or so. I mean, your hands are close to 40. Okay? The pressure would have to be somewhere under 200 or so, but that's not a terribly difficult vacuum to get inside of a sealed container. Okay? So that's a good enough place for us to stop. We'll talk about the equation that defines that sort of stuff next time. Well, that's it.